Okay, today we have a very interesting topic, and you're already familiar with the power flow from the lab. So this will be like a review for you, and also to enhance your theoretical part on the power flow. So what you had in the lab is a power flow that you conducted through the software. So today we will go through the theoretical part of it. We want to construct, I want you to focus today on the construction of the power network equations. So what's the Y bus and Z bus? These are terminology that you will find them a lot in power systems. They're called Y bus and Z bus. The admittance matrix and the impedance matrix. So this is called the admittance matrix, and this is called the admittance matrix, and this is the impedance matrix. We use the admittance matrix in power flow, and we use the impedance matrix in fault analysis, chapter 7. So this will be chapter 6, and this will be chapter 7. Z bus is basically the inverse of Y bus. So it's just the inverse of the Y bus. So if we have the matrix here, we call it Y bus. The impedance matrix will be the inverse of this one here. So this will be, I would say maybe I need to put this as, okay, so this will be Z bus. So the inverse of this one here will be the Z bus. So we just inverse. So the idea here is to convert to find Y bus, and then we invert it. We invert the matrix by matrix inversion. Then you get Z bus. Okay. Then we'll discuss the Gauss-Seidel method. Is one of the iteration method. Are you already familiar with Gauss-Seidel in numerical analysis? Correct. In numerical analysis, you had Newton-Raphson and you had Gauss-Seidel. Correct? Yes. Okay. Thank you, Hamid.
Yes.
All right. So in modeling of power systems, you're familiar with the normal operations of three-phase systems, usually balanced. Okay, so that is why we put them as a single line diagram. So we call it as a single phase system. But this will be as an equivalent single line. So we call it a single line diagram. So when you see this line here, it's a three-phase line. But because it's balanced, so therefore the phase A will be similar to phase B in magnitude, of course. We're talking about magnitude. And the power, what you see, the power of the bus is for the three-phase, not single phase, for a three-phase. So this is also for the three-phase. Okay. The voltage, what you see here, is line to line. So always when we talk about three-phase system and we mention the voltage at the bus, so that is line to line. Okay, so when we say 66 kV or 132 kV, that is line to line voltage. Okay, so this is the terminology that I would like you to know before we go on with the others. And also you are familiar with the Y bus, with the bus. When we say a bus, is a node in circuits. Okay, so the nodes in circuits are called buses here. That's what we mean by buses. That's what we want to measure. We measure the voltages, we measure the current, we measure the power, if any. Okay, so that's what we want, where we want to measure. If we have a load, of course, therefore this will be a bus. Sometimes we just have a T bus in between. This T bus, sometimes we just draw a T bus in between, like this one here. So we put a T bus here like this. So this will be three buses: bus 1, bus 2, and bus 3. Okay, so this would be a bus. What we want to do in here, we want sometimes to. This is a bus will be, of course, in a substation. then we can have transformers in there to boost or also to connect it to other areas also. Although there is no load on this, we call it T-bus. There is no load. It's just a transfer from one side to the other, or we transfer it from this area here to the other area. Okay, by using transformers or shunt capacitors, so we can do a number of things here on this bus. And this bus, although there is no load, also we call it a load bus, although it's a T-bus, transfer bus, but it is also considered to be a load bus. And that's what you had in the lab. You're already familiar with the lab. So what are these buses to be to know? These are three-phase buses, as you can see here, and let me put this in red color. These are three buses. There are pipes. These pipes are connected. Of course, pipes are conductors, okay, made of copper. And these are connected by the three-phase lines. You see, each phase is connected by one line, as you can see here. This is one connected to this one here, and this is another one, and this is another one. Three phase. So we have three. So this will be considered as one bus. Three phase will be considered as one bus, and that's where we draw it like this here. That's where we draw it here. Okay, or this one here also. In reality, it's like this. What you see here, the one that I drew here. Okay, so that is in reality, it's like this. Three conductors connected to, of course, the lines here. And then it will go, of course, to transformers or capacitors. That will be a substation. Now we call this outdoor. This one here, what you see is outdoor. It's the same concept, same thing here, but we can put it as indoor. So this is one, and this is two, and this is three also. These are also buses. One bus, this will be considered as a bus. In a substation could be more than one bus. 6 kV is a bus. 132 kV is another bus. We cannot connect 132 only with the 66 only through a transformer. So it's from one bus to another bus. Okay, from 66 bus to another bus. So this what you see here. So again, now this is indoor. Okay, this is what we'll see. The buses are indoor, and this will be outdoor. What you see here. Okay, all this substation is outdoor. Now, the electric utility Kahrama is mainly now is building all indoor now. Now, what is new, any new substation will be indoor substation, and they get rid of the outdoor as much as possible, and we still have outdoor substations. In a DEFNA, for example, you can when you go to the university, okay, on your left-hand side there is a substation, okay, opposite to the close to Almira, that will be outdoor substation. On Qatar University campus, it is indoor substation. This indoor substation feeds the university campus and also feeds Lusail, not Lusail, Loloa, the Pearl. Okay, so from the university substation there, the cables underground now, goes underground to Loloa, to the Pearl. Okay, so that is another substation, and that is indoor substation. So you will not see these, what you heard, but you will see these indoor. Okay, so we call these buses. And when we draw it again, just think that we draw only one line. Why? Because the other phases will have the same magnitude of current and of power. But then remember now the power which is here, this power here is for the three-phase. Okay, the power, the indicated power is for three-phase power. So we don't write for one single phase and then multiply. So what the power is for the three-phase, and what the voltage is line to line. Okay, so please make sure that you understand the terminologies here, what we discuss. Now the conductor for 132, this picture here, I took it in Qatar University campus. So that's the substation there. That's what you see here, the substation. This is the substation close to the medical college, College of Medicine, Kulliyat al-Tibb. So that's the substation belongs to Kahraman, by the way. It does not belong to Qatar University campus, but it's inside the campus. But it belongs to Kahraman. So Kahraman engineers come to the substation, and the key is with the Kahraman. It's totally controlled with Kahraman, nothing with Qatar University employee. Okay, so these are so. All right, so what is you see here, this one here, we already talked about it, which is what the conductor, transmission line conductor, overhead transmission line. That's what overhead transmission line, that is what you see here in these. Okay, overhead transmission line. These, which goes to from where Qatar University campus, for example, to the peril will be underground. So this will be underground, and it looks like this underground cable. Okay, so it's indoor in the room, and then goes from the room. It goes outside, of course, underground. Okay. As you can see here, this is insulated PVC, insulated cable. This is underground cable. These are not insulated. Overhead transmission line are not insulated, as we can see here. These are not insulated. Okay, which is aluminum, all aluminum, all alloy aluminum. And it's very light, as you can see the hand here. It's very light, very light. Barely you can feel the weight of this one. So it's not heavy, which an advantage that we put it overhead lines all the way, thousands of kilometers, with the support, of course, with the tower, with towers. This one is heavy. Okay, for every high power, it's usually not underground. The question is it underground for high power? It is underground for high power, yes. So this is 132 kV, and this is also 132 kV, same. Okay, so we use it, but when we use it if we want to go underground. For example, we're going to the Corniche or to the city. Okay, so you cannot have overhead transmission lines. Okay, so underground or overhead transmission lines, they have same. So it's not. We can have 400 kV, no problem, underground. But it looks, this is heavy, you see, this is heavy, so it's underground, of course. It's paved. There's so many things that they need to put it. They don't just dump it in there. They need to make also a caution for this one here to be underground. So make it make it not bending. So it's not bended. So make it straight. As you can see here, this is stranded of copper. A number of strands, as you can see, and we discussed these strands. This is the insulator. We need to erase this one. This is the insulator, as you can see, insulator. Okay, and then also there were this also is cooled by oil. So pressure with the oil here, so therefore this will be oil in here, close to this one. Okay, oil. It's called oil impregnated. So there is oil with the pressure of oil that we can cool the conductor. While this one here is not insulated, so the air is the cool or the cooling environment for it. Okay, so the cooling tool or the cooling environment, or it's cooled by air. So this one is cooled by air, while this one is cooled by oil, impregnated oil. Okay, and it's heavy. So this 132 kV, 132 kV, and these are in the Qatar power system. That was what we use. Now the three types of buses, we already also familiar. Now remember, now this is, if you don't know, please raise your hand, okay? Because this you already have it in the lab. So we're just going through them quickly as, but please, if you don't understand, just make sure that you raise your hand. And okay, so we already have what, three types of buses in power flow. We use them: generation bus, or we call it PV bus. PV bus or constant voltage bus. Okay, not necessary to have a generation. It could be, well, of course we have a generation. We must have a generation because we need to specify the voltage and the power. It's called generation bus. Okay, voltage and the power. So we call it constant voltage. So they set it. And then we have the load buses, or we call them PQ bus. So here we call it PV bus, which is power and voltage. We must specify the power and voltage. So the power output from the bus. What's the power output in the bus? Okay. And the voltage, of course, because the generation, we need to fix the voltage. Maybe 1 per unit, or 0.95 per unit, or 1.05, etc. In the PQ bus, so this is what the customer is, where the customer is, the shopping centers, the industry, where they consume power, real power and reactive power. So we call it load bus, or we call it PQ. And then the third one is the reference bus or slack bus, or we call it also swing bus. In some textbooks you will see swing bus. So this will be voltage and angle. Here the others there will be determined, the angle will be determined later, like this one here, Q and angle. So what do we have here in the power systems? We have power. Where is this? We have power, P and Q. We have the voltages. We have the angle. 4 parameters we need to find for every bus: P, V, Q, and delta, or V delta, P, and Q. In every bus in power systems, think of the 4 parameters that we need. We need the voltage of the bus, and at what angle? The angle of the voltage, of course. And then what's the power through this bus, whether it is out, in, whatever. Okay, load bus, load P and load Q. Okay, for every bus we need this: PQ, V, delta. So the buses here, as you can see, these are the one which is specified, must be specified. Must be specified. It must be specified. So PV, PQ, and V delta. So because we have other buses, therefore, what is left? Left is PQ and the slack bus. Why is the reference bus? What does it mean? It means that if you see now we have what? We have load and we have generation from here. So this generation is already determined now. Plasma fantas, for example, we want it to be maybe 20 megawatt or 100 megawatt. Okay, so we specify Al-Wajba maybe 50 megawatt. Ras Al-Afan will be maybe 400 megawatt, and so on. So we need to specify. One substation is okay. That's the load, and then we run the load flow, of course. The slack bus will be the difference now. If the load is increased or decreased, what about the losses? This will be taken care of from the slack bus. We did not specify the P. So the rest will be specified by the reference bus or the slack bus. The rest of what? The rest of we already know the generation of the substations. We already know the load, okay, determined. And then also the losses, when we run the load flow, the losses will be there. So to balance the system, generation must equal load and losses, where the balance will come from the P of the slack bus. Okay, P and Q, of course. The slack bus takes the responsibility of balancing the system. The generation must equal the load plus losses. Okay, there is no reserve for this. You cannot generate more and the load is lower. The generation must go down if the load goes down. Okay, so there is no reserve. We don't reserve the power line. Okay, whatever you consume must, and the losses on the transmission lines must be supplied by the generation and the slack bus. So if you already fixed the generation, then the slack bus will take care of the rest. Okay, what is left will come from the slack bus, and this usually is the big one. Okay, the الأخ الكبير time. Okay, takes care of to balance the system. Okay, so it takes care to balance the system. To balance means that we generate more power. Okay, so this must go and must be the big one, big substation. Okay. Okay, and this the V and delta again, and Q and delta will be for the generation and PV bus. Okay, do we need to know this? Yes, you need to know this. So what is the input and what is the output? So we call this input. Okay, we call this input. All right, and this we call this output. Okay, this is in. This is input and this is the output. Input what means that you need to enter the P and V, P and Q of all these buses. What's the voltage of the reference bus? What's the angle of the reference bus? Now we usually put this as 0 angle. And then all the angles here, what you see, when you say this, for example, 0, and this, for example, is -5. What does it mean -5? It's -5 with this one here. The difference between this one and this one. This is what we mean by -5 degree, or -3 degree, or -0.1 degree, so on. Okay, so it's the difference between this, what you see, all the buses, the angle, and with the reference bus. Okay, with this angle here. So with respect to the reference bus, to the slack bus, all the voltages with respect to the slack bus. Okay, all the buses, again, now all the buses with respect to the slack bus. So if you put the slack bus is -5, also will be not necessarily 0. Okay, but this is for convenience, of course, even if it's -5, so we set it as 0. There's no problem. Okay, because it's a reference bus from the rest. If you set it at -5, the rest also will be with respect to -5. Anyhow. Okay, so these are the 4 parameters that we need to know for every bus in power flow. Now, this is an IEEE 9 bus system. By the way, these are we called IEEE. These are standards. Why we use these IEEE 9 bus? And because the researchers can compare their results. So this is a standard 9 bus, 14 bus, 57 bus, 114 bus, as you go on. And if you do your master degree or PhD, they will also use 9 bus system. That's okay as a start. And then you can go on. When will I go on? Continue. If you compare your results with other researchers, and you will see, okay, you get the same results. Okay. Then your system is valid because all the researchers will use one common. Okay, so they have the 14, they have the 30 bus system, and they have the 9 bus system, so they can use it. And then when you read, so you can compare your results with other authors. So that's why we use the IEEE 9 bus system or the 14 bus system. It's common. Okay. All right, so this is a 9 bus system, as you can see. This part here, what you can see, let me put this in maybe this part here with the transformer inside is one substation. Is inside this transformer, although you can look at the transformer here is in between, but it is one substation. So this should be close to bus number 2. So that's the substation, the transformer. And then it goes, substation could be maybe Ras Bufantas. Okay. And then it goes to Al Wakra. So this will be Al Wakra, it's bus number 7. Al Wakra. So this all the way here from Ras Bufantas to Al Wakra. Although you can see it in here just for convenience to see the transformer in the middle. But geographically is not in the middle of the transmission line. It is geographically, it is where it is with the bus. Okay, it's with the substation. Bus number 2. Because in the generation, we need a transformer. The generation, the voltage of the generators, the output of the generator will be about 6.6 kV or 11 kV at most. Then we want to raise up this 11 or 6.6 kV to 266. So that will be 10 times, or to 132 kV. That will be even 20 times of the voltage of the generator. Okay, the output of the generator. So the generator output, the voltage is 6.6, but the same power. Therefore, you will see out of the generator, the cable is like this. Very big cable coming from the generator, very big. Okay, the diameter is big, but it's for short distance only. Comes there for short distance, goes to the transformer, and then you raise up. Why large cable? Can you anyone tell me why we need a large cable for the 6.6 kV? Why? Abdulaziz Bouazza is here or not here? Not here. Abdulaziz Ahmed is here or not here?
نعم دكتور موجود.
تفضل. Why do we need مين موجود؟ بوزع ولا عبد العزيز؟
لا الإبراهيم.
تفضل يا عبد العزيز. Why do we need?
Maybe as we increase the voltage, the current will be decreased.
Very good. So for the lower voltage, 6.6 kV, we need very high current. because the power will be the same. The power which leaves Raj Fontas goes also to Saeed.
So that's why we
Okay?
need a thicker cable.
That's why we need a very thicker cable, which is the diameter will be very huge. So that's why we only bring it to the substation there, very close, of course. The substation is in one substation. The generation and the transformer, this one we're talking about, is in the same substation. So we only bring it to the transformer, which is very close. We don't want to make it loud. So this is very close to bus number 2, the transformer. Although we draw it here, but this is just for convenience to see. Similar for bus number 3, as you can see, we draw it in the middle, but geographically it's not in the middle. This is with just outside the building, the transformer, just outside the building of the generation. The generators are indoor, and then the transformer is outdoor. So just outside there, very big cable, and then as you raise it up to 220 kV or 20 kV or to our 66 kV, so 10 times or 20 times or 30 times, because that's only 6.6 kV out of the generator. Then you rest up, therefore the current will be low because the voltage is high. Same power, VI equals the power. Of course, power equals voltage times I, just cosine theta. So the cable will be small, as you can see the picture before, with it's very light, very small, 132 kV. That's enough because it's 132 kV. So the current is low. All right. So this is a 9-bus system, and this is the way you draw it in your project when you draw the substations, the buses. Okay, in your project you need to draw, of course, and this is the way. And you're already familiar with this. What you put in there, you put there. So and what you put in bus number 8. Bus number 8 here is a load bus. Why? Because this is a load. Bus number 7 here, as you can see, this bus number 7. It's also called the load bus, similar for PQ, but the PQ is 0. So P and Q is 0. This is a T bus. So what do we need to specify at bus number 7? What do we need to specify at bus number 7? We need to specify P and Q. So what is P and Q? 0 and 0. 0 here and 0. You put 0 and 0. So we know this is what? A T bus. يعني على الطريق بس. ماشي. اوكي تفضل يا اوكي who raised his hand عبد العزيز or who? تفضل. Go ahead.
بلال دكتور.
بالغلط. Okay. All right. So this bus number 7 we call it a load bus. Okay. Why? But the load is 0. This bus number 6 is a load bus, but the load is this part here, 90 megawatt and 30 megabar. And remember, these are all 3 phases. Huh? Okay, so this is bus. And also when you see in these 9 bus system, now we have 9 bus systems, they're all connected together. It's like a ring. So it's like a loop. Although we draw it مربع, okay, square like this one. So they support each other. Any problem, and not any. Well, any load increase from any bus, other generators will take care of it. So maybe bus number 2 will be raised a little, and bus number 3 a little, and bus number 1. Okay. So the power system is interconnected together. It's a loop. Okay. Then it becomes stable and secure also. But when it comes to your okay, that's it. That's it. So okay. Again, now the power system is like this. I don't want to confuse you again. All right. Now we want to write the Y bus. Now we know. Now we want to write the formulas. What formulas? We will use it for the load flow. Now this is the theoretical part. Now I would like you to focus. You are engineers and you are not data entry. You are not technician. Because you are engineers, you know the theory. you need to know the theory behind what you're doing in the computer, the theory behind this. That's why engineers are different than technicians, because the engineers design things and they know the theory. The theoretical part is and the math and the theoretical part is high. Okay, is extensive. With the engineering disciplines, all engineering disciplines will have this. Technicians will get less math, and then we have technologists. Okay, it's not College of Technology; it's College of Engineering. All right. So what we have in here. First of all, this is given. Now this is circuit number 1. Okay, so not circuit. This is circuit 1. Okay, circuit 1. Basic circuits that you already had before. So it will be given like these. So this is an ohm, for example. Just any numbers. Okay, any numbers here are written in ohm. What we need to do is to convert it into nodal analysis. So what do we need to convert this part here to make it nodal analysis? You remember now we say for in nodal analysis we calculate the current. So we want to find the current. We want to calculate the current. So we say V1 minus V2 over this part, over the line in between. This is what you do in nodal analysis. V1 minus V2, node 1 minus node 2, over the impedance between the two nodes. V1 minus V3 over the impedance between 1 and 3, and so on. That's what we do, correct? So we can work it like this, straightforward, V1 minus V2, etc., over this one. Or it's a convenient to transfer into current, to transfer the voltage into current and make all the what is in between here, we make it in parallel with the source. Okay, so this is bus number 2 and this is bus number 1. So we convert only this part here, only this part from one part here. So we can convert this part here. Okay, so we convert it into this one. Why we need to convert? Just for convenience. If you can work it on the other side, it's okay. But both sources converted into current sources. So we can say we add the impedance or the admittance. We add them. Okay, so we add the admittance here, converted into admittance. That's why we call it Y bus. So it makes that convenient to convert it into admittance. So both sources are converted into current. And remember now, okay, so please review how to convert a voltage source into a current source. So this is straightforward unless you have a question that we can answer. Okay. And remember now, when you convert, if you want to convert this one, if you convert this one here, how do you convert it? You will just this, so you will only take this part here because I'm converting from 1. Therefore, I can just draw it like this and get rid of this, of course, and make this is current. This is the way we do it. Okay. So we did not convert J3 Siemens. We did not convert it. Why? Because we did not. We only work it from 1 to 2. Similar from 3. So you hold 3 here, and then you bring it down. Okay, so you bring it to the earth. This one here to earth, and you make this one here as only 1 as a current. So this is what you do. And also we had students that they make mistakes when they do this part in the middle. So what you do, you fix this bus, this node, And then you bring this down all to the earth, down all the earth. And you make this part here, the voltage, converted into a current source. How we convert to current source? V over Z. Okay, so V over Z. Z is in between, which is this one. Okay, so that is the way you will do. Now it becomes easy to, after conversion to current sources, now becomes easy to do what? To convert it to form the Y bus. And the Y bus is simply like this. Y11, Y12, Y13. You're already familiar with nodal analysis. Okay. Diagonal element is called YKK, called self-admittance. Called self-admittance. That we sum up all the admittances which are connected to bus to node number 1, or to node number 2, and so on. So these diagonal elements, Y22, Y233, and so on, we are summing all the admittances which connected to what? To this. For example, at 1, now we come to this one, okay? To this one now. So we sum this one plus this one. What about Y22? Can anyone tell me now what's Y22? Okay, let me talk the name. Take the names. Abdul Aziz Yahari. Not here. Abdul Aziz Yusuf Dalul.
Yes, doctor.
تفضل يا دكتور.
دكتور حضرتك كنت قاعد you were discussing about how to draw this to convert it to the other
No, I'm asking. أنا خلصنا هذا الشيء. Now I want to find Y22. What will be Y22? What will be Y22? Yes, 1 over Z. Y22. Yeah, Y22.
1 over 1J.
What do we do with the Y22? We sum up all the admittances which connected to 2. So what's Y1J? You add it from here. Okay, so you add this one plus this one plus this one. You add it. Okay? Okay. Tell me, Khalil Khan, are you here? Not here. Hassan Al-Arab, are you here?
Yes, doctor, but I'm not too sure, to be honest, of
what, أيوة.
of Y22.
Huh? Y22. You sum up all the admittances of the 2. We're all connected to Y22. You sum up this and this one, all which is connected to 2. Okay. So tell me Y33.
So for 22, would it be minus 4JS if I sum them up?
Minus 1S plus 1S plus 2S. Yes, this will be J1S at the end. J1S. But I would just tell me what will be the sum. You don't tell me the results. You just tell me what you are summing. Summing what?
So minus 1J plus 1JS minus 2JS.
Yes. Plus
and
this one also.
Plus 3JS.
Yes.
And minus 10JS, or is that not included?
When it's 10JS.
Oh no, it's
not included. Why? Because this is with what now? خلاص. Okay. This is with another bus. Okay, so another node. So you do not include this one. You do not include it. Okay. So how many branches in 2? We have 1, 2, 3, 4, 5. Therefore, you need to sum up 5. Okay, sum up 5. Where is there 5? 1, 2, 3, 4. 4. Sum 4. Okay. You don't sum the current, of course. So we have four branches. Therefore, you will sum 4 branches. Okay. Leif Kanaan. Not here.
Yeah, I'm here.
MashaAllah alayka. Okay, very good. Tell me now, what will be Y33?
We do the same procedure, so it's minus J2S plus J1S minus J4S.
Correct. Thank you. That's it. Very good. Okay, so this is, so what will be Y12, yeah, Muhammad Al-Hariri? Y12.
Y12 G3S.
Okay, so but because it is no, because we say V1 minus V2 over the Z impedance, so this will be Y21 will be minus J3S minus. So we put the off diagonal, okay, minus. So this will be minus. Okay, so therefore this will be Y12 will be minus J3, as you can see here. Okay, this is minus J. Okay, minus J3. Okay, here, this one. So we just put the negative of diagonal elements. These diagonal elements here, 1, 2, 3, 4. Okay, 1, 2, 3, not 1, 2. Okay, we add them, as you can see. All right, so we add the diagonal elements. The off diagonal elements, because we convert this all to this is Y, by the way. Okay, this is our Y. This is Y. Okay, and because we convert it into this into admittance matrix, so therefore we put minus in front of every one which is in the diagonal. This comes, the minus comes from what? From, because we say V1 minus V2 over Z. Okay, so this is because it's a negative. Okay, so that's why we put negative. Okay, so all the off diagonal will be negative. 1, 3 is not are not connected. Therefore, we put 0. We put 0. Remember now, this is 1, this is 2, and this is 3. Okay, and this is 1, this is 2, and this is 3. Now, this, by the way, these lines they come just by blackboard. I did not draw these lines, okay? But when I press like this one, sometimes these lines come up. So this is a function. This is from the blackboard. All right, so I did not draw these lines. Talking about these lines. All right, so we have 1, 2, 3, and 1, 2, 3. So we'll say 1. I need to erase this one. So this is 1, 2, 3. This is 1. This is 2, and this is 3. This is 1, 2, 3. Why 3 by 3? Because we have 3 buses. So 3 by 3 because we have 3 buses. What are these buses? So this one here, 1, 2, 3. 3 nodes, 3 buses, doesn't matter now. This circuit here, we call them nodes. So these are nodes now. We're talking about nodes or buses. So 3 buses, we will have 3 by 3. How many elements? Will be 9 elements. Okay, now if you want 3 by 3, so 3 by 3 is this one. You want Y22. Where's Y22? You will go to from 2 to 2. So it's this one. Okay, can you please say again why it's 0 for Y13? For Y3, because 1, 3 is not connected. There is no impedance. There is no admittance between 1 and 3. Okay, there is no impedance. So 1 and 2 and 3. So why? So 1, 3 is not there. It's not connected. So we put 0. And you can also note here that this matrix is symmetrical. So Y13 equals Y31. As you can see, this is 0 here also. So symmetrical. So the Y admittance is a symmetrical matrix. Okay. Remember, the diagonal elements, we add them. Y12 is always equal to Y21. Yes. Y12 equals Y21, Y13 equals Y31, and so on. Y22, we are summing all the elements into. Okay, so Y33, we're summing all the elements in 3. So the diagonal elements are large than the off diagonal elements. Okay, because we are summing all the connectors, as you can see here. So you can, and then if you work it out, you will get this matrix. Okay. This -7 does not come because of the negative, just because of the large number here. Okay, so it has nothing to do. But this the minus here, because we put the minus in there. Okay, so we put negative. Whatever, if it is negative, we change the sign. We put it positive. So we put negative in front. All right, so this is now 10:50, so I would stop here. Just please register for attendance. I'll just open the attendance for, okay, I will stop recording now.